Good morning, everyone. This is some kind of tutorial, or it's supposed to be, so I hope you'll learn something. But do feel free to shout out if there's something that is obscure or you've got any further questions as we go along. So outline, begin with an introduction, say what Gaussian processes emulators are used for in computer model usage. Then I'll go into some of theory, how you build the emulator, and with a few wrap-up items at the end. So, introduction. What is a Gaussian process? Well, as far as we're concerned for this context, it's a probability distribution for a function. So if f is a function and it's uncertain or random, then for every x, fx is uncertain, so it has a distribution. And for every x and x prime, fx and fx prime have a joint probability distribution, and so on. And we get a probability distribution for the whole function. So it's a big joint probability distribution in infinite dimensions. And so this is sort of the way of drawing it typically. There's a mean function, the red line, plus or minus some standard deviation around it for the dotted blue line. What's it for? Well, we're going to use it in the following sense. We have a model implemented as a computer code, a simulator. Simulator output is a function of the inputs. So we're going to use this model as a way of representing probability distribution for a function. Because when the model's highly computer intensive, people build fast approximations. Approximations are typically called surrogates. And they run the model a sample of X configurations, so they get actual data from the model, and then they approximate to those points, build their surrogate around those points. And the Gaussian process is one way of doing that. It's actually quite an efficient user of the data that you give it. But it's actually much more than just that. And that's why we use the term an emulator. Now I'm going to make this distinction because apparently I was the first person to use the word in this context, so I kind of invented it, so I think I'm allowed to define it. People use it very much more widely than I meant it to be. So we're going to be very precise about this. But before we do that, let's just have a quick look at how the thing works. So here we have a situation where we've got one input, x, and one output. We've run the model at 2 points, at x equals 1 and x equals 5, and we've observed the values of y at those 2 points. With just that amount of training, our emulator is going to look roughly like this. It's going to have a fit that goes through those points, that's the mean function, plus or minus some uncertainty. And the important point to note here is that there is no uncertainty at these 2 points. We do know what the function does at those 2 points. We have run the code at those two x values, so we know it goes through those 2 points. So the mean function must go through, and the uncertainty must go to 0 at those points. And you can imagine what's going on is that you start off with sort of generalized uncertainty and not really knowing too much about where the thing goes. And then when you find a point, you pinch the uncertainty in and harness it to that point, fixing those points. So if you get one more point in the middle there, you're going to pull the thing down and fix it at that point, like putting a thumbtack in, okay? It doesn't lie on the original line, but it lies within the original range of uncertainty. And notice every time you squeeze this uncertainty in, there's a reduction in how much it can grow before you get to the next point where you've pinched it in. And if you get enough points, squeeze it and squeeze it along this line, there isn't anywhere very much for it to go except along that line that is a smooth interpolator of the points that you've got. So now you know what the actual function would have done pretty much everywhere between 1 and 5 because you've got all of those points in there. Of course, outside that range, you're still unsure. Increasingly unsure as you move away from where you actually got the data. But that's fine. If all we want to do is to have a representation, a surrogate for the model in that range x equals 1 to x equals 5, we seem to have done pretty well here. And so we can go on and on. And of course we could do this in higher dimensions. Imagine x is now a plane and you're still pinning those y values at various points and the uncertainty grows between them. By carefully placing enough model runs, we can build an emulator with low uncertainty everywhere we're interested in principle. And when I said that the Gaussian process uses the data efficiently, what I mean is we can typically do that with far fewer data points than other surrogates seem to need. It works for 2 or more inputs, as I've just said. In fact, it can have very many, but that's in principle. In practice, it becomes computationally heavy when we get too many dimensions. So if you've got a model, a simulator that requires hundreds of inputs, there's no point in trying to emulate it this way. But in reasonable numbers of dimensions, this is, in my opinion, the best way to go about trying to get a surrogate or an emulator which is more than that. Let me say exactly why I mean an emulator is more than that. We have a full probability distribution. We don't just have approximation. We don't just have the mean function. We have a full probability distribution. So the emulator quantifies uncertainty around the approximation. That uncertainty I'm going to refer to as code uncertainty, as and when I do refer to it. The mean function is a fast surrogate. You can approximate f for any x you want to. And at every data point where we've run the model, it correctly predicts the corresponding y. It's a feature which almost every other surrogate does not seem to possess. The emulator mean is an interpolator. And it gets the uncertainty right. It not only interpolates through the points, it says, I know where I am at those points. I have zero uncertainty about the function. So all other common surrogates that I'm aware of fail on all of those key properties. Polynomial chaos, response surfaces, neural nets, they are not emulators. Do not call them that. Okay? Please. Let's keep the good word for the good stuff. By the way, this square bracket thing here is a place marker. I'm going to put references in. I just haven't done it yet. I'm used to preparing my talks at the last minute. I've actually overdone it this time. So it may be a bit rough in places, and the references are not there, but they will be in the version that I give to the organisers to be posted in due course. Okay, so what do we use emulators for? It's not just to approximate the function itself and predict the output for a particular x, although of course you can do that. You can also do uncertainty analysis, or what has come to be called uncertainty quantification. Hate the term, but it seems to be totally pervasive. That's propagating the input uncertainty through the model. Predicting f, if you like, with an uncertain x. And of course, we can add in this extra thing because we know the uncertainty of the surrogate itself. We can add uncertainty, code uncertainty, into this calculation. So we actually quantify uncertainty, more of it. Sensitivity analysis, an important tool, understanding how the inputs affect the outputs. Again, you can do this. You can do all of these things. They all follow through once you've built your emulator with relatively little extra work. And finally, the task of calibration or inversion of models, which I think we'll be hearing about later. However, it is crucial at this point to recognize that models are wrong. Let's look at that. All models are built to represent a reality, some real process, but models could never be perfect. Otherwise, they wouldn't be called models. They would be the process. Okay? So if we know the inputs, that output from the model, even if we've got the right inputs, will still differ from reality, and that's going to be called model discrepancy. So the red line is the mean function of my emulator, but red line is the actual true simulator. The green dotted line is the true reality. They are going to differ from each other. So when we analyze this using the Gaussian process type tools, we first of all need to split the inputs, so we recognize those ones which are things to be learnt about through the calibration process, and those which are defining the various characteristics of the process that we're trying to simulate. So we're going to write reality as a sum of the function, the simulator, and the model discrepancy delta. And we're going to model delta as a Gaussian process. So it's another use for a Gaussian process. It's another function, so there's another thing we can put a Gaussian process on. And notice that discrepancy depends only on the x part and not on the calibration parameters. The calibration parameters, if you like, fixed by the world, but x is the thing we vary. As we vary it, we get different instances of the simulator. So now we can use the emulator plus emulating the discrepancy to predict the reality. And if you do this right, you can learn about both the model discrepancy and the calibration parameters from observational data. But you don't do it unless you recognize the existence of the model discrepancy. And there's an important reference there which will be in the final version. Okay. That's what, if you like, all of that was introduction. That's why we do all this stuff, what we can do with it. For the benefit of the more mathematical minded here, I'm going to try and do some mathematics. So formally a Gaussian process is what we call a stochastic process, but that's a bad term in this case because everybody associates stochastic processes with things that are developing in time. Our functions, their arguments can develop in space or whatever those x's represent. So I just call it a probability distribution for a function, and we can represent just about any kind of function in this way. We call it a Gaussian process because it's Gaussian, because everything about it is a normal distribution. It's a big extension of the biggest kind of multivariate normal distribution you can imagine. So formally, f is a function. Its domain can be anything, but usually we'll have Rp. Range can also be more or less any Euclidean space, but we usually have it just one dimensional. So simulators often produce many outputs, but usually we're interested in one at a time. So our function is a Gaussian process with parameters m and c if, as it says here, any given x, the simulator, the function output at that x is normal with mean m and variance c xx. But then when you extend to more inputs or more points, any n points have a multivariate normal distribution with mean vector given by all the m values and the covariance matrix given by all the possible pairs of c values. So then we get an n-dimensional multivariate normal. And the definition of the Gaussian process is that this is true no matter how big n is. And that's the natural extension from finite dimensions to the infinite dimensional function space of a Gaussian distribution. The parameters we use, m is the mean function, and that can be anything, any function, on the same space, obviously. The covariance function, though, must be positive definite, in the sense that for any x1 up to xn, that covariance matrix I showed you before must be positive definite. And this has to hold for all possible sets of x's, no matter how many. Stationary case, we often use this where we take the covariance function to be a function only the distance between x and x prime. So sigma squared is a variance and r is a correlation between x and x prime. So r is going to be 1, r of 0 is going to be 1, and there, for all other larger values of its argument it gets to be less than 1. And that correlation function is also said to be required to be positive definite, and there's a function which says this is true if it's a characteristic function of some probability distribution. And the one we use most, and what I use most, is the Gaussian correlation function. So this is the characteristic function of a large multivariate normal distribution in the space of the x's. So the Gaussian correlation function, as I said, is a very common choice, but there is something called the Mattern correlation function. There are various others. I'll explain later why I tend not to use the Mattern, although there are a number of people that do. Important properties of this Gaussian process. If we have a Gaussian process, then if I condition that Gaussian process on knowing the value at any number of points, and then particularly let's just start with 1 point, so the function f given the value fx at a single point x is still a Gaussian process. Its mean function changes, its covariance function changes, and the point about that is they achieve this effect that we talked about earlier. That mean function will equal fx at x. At all other x values, we don't know what it's going to be, but there'll be some uncertainty about it. But where we've made this observation, where we've got the conditioning of a particular x, f of x, then the mean function passes through there, and the covariance function gives you a zero variance at that point. So that's what we were seeing in this pinching of the function uncertainty down. At every point where we've observed it, the function must pass through that point with zero uncertainty. And of course, by induction, you can do this, extend it to many, many points, as we did, starting with a couple of points, 3, 4, 5, etc. And these, as I said before, are key properties of an emulator. And they're essentially natural properties of any proper representation of uncertainty about a function. It's just that most surrogates are not that kind of thing. They're not a proper probabilistic representation of uncertainty about a function. Another important property is what I call linearity. Basically, just as the sum of two normal random variables is a normal distribution, if they're independent, even if they're correlated, but they're multivariate normal. Same thing happens here. If we start with the Gaussian process and we apply a linear operator like this integration with respect to any function x, g of x, then we're going to get a normal distribution for that integral. It's a very useful property, provided the integrals converge, of course. You know, all the mathematicians worry about these criteria. And the meaning of this in terms of what I showed you before is that when we're doing uncertainty analysis, our inputs are uncertain. So the inputs have probability distributions. So if g is the density function of the inputs to represent the uncertainty on the inputs, then that integral is the expectation of the output. Other integrals represent other properties of the uncertainty distribution of the output. And this means that we can go straight through to producing the normal distribution for that, which quantifies the code uncertainty about the expected output. Again, we're giving a more complete quantification of uncertainty. With any other surrogate, you can do the integration with the mean function, and you can get an estimate of the mean with the uncertain input, but you don't get the code uncertainty. Same thing with variance-based sensitivity indices. Differentiability is another important property of the Gaussian process. So if f is a Gaussian process, then we apply some differential operator, and that the derivative of the function will exist almost everywhere with probability 1 if the m and the c are differentiable in the required way. And then the derivative of the function is another Gaussian process. So again, this is an extremely useful property in some situations. The Gaussian correlation function is infinitely differentiable and is used therefore to represent functions that are analytic. Most computer simulation codes that I've worked with have this property. Some of them have non-differentiable sort of changes of direction or even jumps within them, and clearly then this would not be appropriate. The Gaussian correlation function is great for all kinds of smooth computer codes, whereas the Mattern has no derivatives, and therefore it represents functions that in principle are not differentiable anywhere. So again, the benefit in terms of working with computer codes is that we can get, if you like, an adjoint automatically. We can get derivatives of the function as soon as we've built the emulator. We can immediately emulate the derivatives of the function. So building the emulator is the big question. How do we get about doing this thing? It's a Bayesian process. We start with a prior Gaussian process, representing prior knowledge that we hold about the simulator before we do any model runs. Of course, it's unrealistic to say you could ever have information about this simulator before you do any runs, because people always have run it, but you usually don't make use of that information in a formal way at this point. So we will generally use relatively uninformative prior distributions at this stage. Because we're going to learn, we're going to do some runs. We then condition on a number of runs, enough runs we think, if possible, to give us a good emulation of this function across the space of inputs we're interested in. In practice, if the simulator is really slow, we may not be able to do as many runs as we would like. Nevertheless, even with a limited number of runs, we are going to get the best kind of representation of that function that we can using a Gaussian process. So we condition on the data in exactly the way I showed you to produce the posterior Gaussian process. That's the emulator. So when we're setting this up, we need to set up the prior Gaussian process. And the Gaussian process has a number of features. As we know, it has the mean function and the covariance function, so we definitely need to do those. Actually, there's also the Gaussianity, the normal distribution part of it, which people often question. It's a representation of knowledge or beliefs about the function. You're saying that at any particular point, I have a certain expectation, M, I have a certain uncertainty given by C, and the probability distribution that represents that uncertainty is a normal distribution. It's an assumption. It could be a strong one. But think about this. If you can get enough runs to pin that function down very accurately, it doesn't matter whether the uncertainty is normal or not, because it's small. It doesn't matter what the shape of the probability distribution is if you're really sure about where it is. It only becomes important, as I said, in that situation where you've got a large time to run the simulator, you can't get many runs, and so you're having to accept that your emulator has appreciable uncertainty over parts of the space that you're interested in. And then it may matter whether that probability distribution being normal is a fair representation of what we believe. And then we may need to think about making transformations that would make that better. So the main thing we do is to specify the mean function, the covariance function. The mean function can represent genuine quantitative expectations about this thing. So you could say, even before I see any runs, I think that at these sort of inputs it will produce an output around there. And that may be based on your knowledge of the process that you're trying to represent by this simulator. So if it's available, that would be great. In practice, we generally use a simpler formulation. We represent M in this regression function kind of way. So you've got H as a vector of regressor functions, or functions that represent movement in the space, and beta is a coefficient of unknown hyperparameters, regression coefficients. For instance, in this case, we've got a constant term alpha, and we've got a gamma times x, which gives you a separate gamma coefficient in the vector for every one of your inputs in x. And that will represent a belief that in some sense there's a gradient with respect to each of the x's. As that x moves across its range, the output is expected to move. Otherwise, why have you got that input in there? Okay, so you're going to expect some kind of movement, and at least we ought to include a linear part of that to capture some of that dynamic in the output. We then give beta a non-informative, uniform prior distribution. Again, you could put in something informative. You could say, for instance, that as this input increases, I would expect the output to increase. Then you'd be able to say, well, I think that corresponding beta coefficient ought to be positive. Generally, we allow the data to tell us about this because we're going to get a relatively large number of runs to fit some kind of model of this kind. So we're going to learn about those coefficients pretty well anyway. Putting prior information about them is not crucial in general. Notice, by the way, now we're into hierarchical modeling in Bayesian terms. So we have two levels of modeling. We have the Gaussian process, which represents the function given these hyperparameters, the betas, and then we have a probability distribution on the betas representing uncertainty about that. There's two stages in this probabilistic modeling. When we go to look at the covariance function, again, typically we could use this to express any kinds of genuine beliefs about the function. In particular, how uncertain we are about certain parts of the space. For instance, we could say we believe it's going to be more uncertain in this part of the region than in that part. But in practice, again, we generally use something simple. Stationary covariance function formulation, Gaussian correlation function, because, as I say, that seems to work for the sorts of functions that I typically experience. The lambda matrix here is going to be diagonal. Each of those little lambdas is called a correlation length. So we've now got a bunch of more further hyperparameters. We've got sigma squared and we've got the lambda vector. So we still have a hierarchical model. We still have the Gaussian process at the top. Then we have beta, sigma squared, lambda as hyperparameters below that, which are given prior distributions. And as again, these are typically given uninformative prior distributions. Let's let the data tell us about these things. However, when it comes to these parameters, and particularly to the lambdas, it really is a good idea to think about prior information. As we'll see later, we got some learning to learn about these parameters from the data, and that learning is greatly improved now if you put strong or useful prior information in about these parameters. There isn't so much information typically in the data that we've got. So we should think about this. A prior distribution for sigma squared will represent beliefs about how much this function varies with x, over and above what we're capturing in the mean function. So we may be getting some linear trend in the mean function, but obviously it's not going to be a precisely linear response to that input. So what's the extra part? What's the extra variability in there? And the lambdas, the correlation lengths, represent how fast the thing can change as we move x. So how wiggly it gets. If you've got a short correlation length, it's going to wiggle more. Or you're expressing a belief that it's going to wiggle more than with a long correlation length. So having some notion about how responsive the function is to different kinds of inputs would be extremely useful for putting in as prior information. So what does a Gaussian process look like? Well, in the top left, there's some realizations from a Gaussian process with sigma equals 1, lambda equals 1, and a constant mean. So all those different colored lines are different realizations from the same Gaussian process. If I increase the correlation length to the right there, I just slow down all those wiggles. Actually, all I've done is taken that picture, doubled it in width and truncated. Because that's essentially what we're doing. Okay? So if I have a longer correlation length, things wiggle slower. If I have a bigger sigma squared, well, again, I took just the same picture I did this, okay? Because that's what increasing the variance does. It just increases the amount of variability in there. So the range over which it changes. So those parameters are describing important features of the function and your beliefs about that function. If you can put it in at prior stage, that's useful. Obviously, we're going to try and learn about them from the runs that we've got. And that's the fitting process. So deriving the posterior emulator is now no longer just a matter of conditioning on those data points. That's just the top level of our uncertainty. Underneath that, we've got these uncertainties about the hyperparameters, and we need to use the data to learn about those as well. So we've got a hyperparameter vector theta, which contains beta, sigma squared, and lambda. Conditional on theta, it's just a Gaussian process, and we can just condition the data to produce that Gaussian process, posterior Gaussian process, which is this part here. But then we also need to learn about theta from the data, and that's the harder part. That requires genuine Bayesian updating, and can be, particularly when we've got a large number of hyperparameters, it can be a complex process to understand and compute that posterior distribution for the thetas. And this again is where putting that useful prior information in can make a difference. So, I'm already into my finally. Got loads of time left, so we've plenty of time for questions, guys. Or early lunch, or whatever. Is it lunch? No, it's not lunchtime, sorry. Early coffee, whatever. It feels like lunch to me. Okay. That's because I've been working on this damn thing so much. Right, okay. It may be interesting just to bear in mind that there are other uses of this Gaussian process thing for other functions. It's a generic tool for modeling functions. And if you're researching this, if you're wanting to follow up references, I thought it'd be useful to give you some other references about other times it's been used to represent other kinds of functions, because you may pick up other tips about it from that. So these are all applications that I've done. The first thing I did was non-parametric regression. So in a classical statistical regression problem, you've got a regression function which is the mean of y given x, and let's not say that that has to be any particular constrained form like a linear or quadratic or whatever. Have a non-parametric regression. Let's represent that regression function as a Gaussian process. And that was my first use of Gaussian processes, way back 1978. And not much happened after that, but gradually people began to cotton on to these things. The next time I did it was to represent essentially an arbitrary function that we're trying to integrate numerically with quadrature. So your runs of the model now become simply evaluations of the function. And in quadrature you evaluate the function at some points, and then you use a formula to get the integral, which is essentially like putting some kind of surrogate in and integrating that. Well, if you do it with a Gaussian process, you get a posterior distribution for that integral, which is normal, which actually gives you your uncertainty about the integral based on the number of runs you've done or number of function evaluations. And as you get more function evaluations, you reduce your uncertainty. So that was kind of nice. That was the next thing I did. And that's since, I mean, there were other people doing something similar at the same time, but now there are a lot more people doing that. They call it probabilistic numerics, apparently. So Gaussian process is essentially on arbitrary mathematical functions in order to do numerical analysis of some kind on them. I used it to model the radiocarbon calibration curve with a student. There's another application in which we were interested in some kind of geographical problem where we've got pollution spread around some space, but the uncertainties and the way that this was spreading around is non-isotropic. So they proposed a mapping from that space to a nice space in which things are isotropic, and that mapping is another Gaussian process. And the last one there, another thing I've been doing a lot of, and more lately, is eliciting expert knowledge in the form of probability distributions. In our computer models context, this is an important tool to get the input uncertainties. Again, most of the UQ literature assumes you've already got a probability distribution on your inputs. It never talks about quantifying that uncertainty. But that's an important step. And expert knowledge elicited is actually a very common tool to get probability distributions for inputs. The last 3 days, the reason I haven't been here until today, the last 3 days I've been teaching a course on that. And one of the things I did some time back, again with another student, was you have a function. Again, it's a bit like the probabilistic numerics. But now what you learn about that function, this function is the expert's probability density function for this thing you're interested in. You don't observe the density function from the expert. You don't ask the expert to tell you what the density is at certain points. You ask the expert to tell you what's the probability this thing might be above here or below there. Okay, so you learn about some integrals of that function. Great, because integrals are Gaussian, everything's Gaussian. So we did that as a way of finding a posterior distribution for the expert's distribution was. It's not being used, it's too complicated perhaps, but it's kind of a neat idea. And of course others have used them for many more. And I'm going to apologize now because not only do we not have the references, but when you get them, they'll all be references to things I've done. And there's a very good reason for that, which is that I'm a lousy scholar of other people's work. I just can never remember where I read something or who did it. And that's a terrible admission, I know, in an academic, but it's true. And so if I wanted to add all sorts of other references, it would take me a long time to go and search them out. So I leave that to you. This is what I normally do when I write papers. I leave it to the referees to tell me what I should have cited. And if it's terribly damning, it's been done before, of course, I've wasted an awful lot of time. But because I'm such a quirky kind of guy, I tend not to do things that other people have done before. I do things that people may not be interested in doing, but that's another matter. So there we are. That's the talk. I hope it's a useful basis for people to start to understand what Gaussian processes are, why we use them, and why they produce something which is special, called an emulator. It's not just a surrogate. Thank you.
Thank you very much. So we've got plenty of time for discussion, which is great. So please chip in. Yes.
Tony, the simulators I work with, they have very complex outputs, so different variables and time series are produced by the simulator for all the different variables. What would be the strategy for emulation in such circumstances?
That's really hard, actually. We have tried to write some papers about emulating a dynamic model. It's a very interesting, very challenging issue, because what's happening is there is a function which is the single step of this thing, single time step, which you maybe in principle continues, but in reality it's going to be discretized. So there's a time step, and that's a function that does that, and that function is iterated to get the time series. And if you can emulate that step, you in principle can have a really good handle on how the thing is going to evolve. If you don't do that, you've got a much bigger, much higher dimensional problem to handle, because you've got all these different points that you could have. Okay, maybe the step in the state space is still quite high dimensional, but if we could do that, it's good. The problem is iterating the emulator, because that becomes just almost as much work as running the original model if you're not careful.
That's your biometric paper?
What's it in biometric? I don't know. I don't even remember my own papers. I would have to look them up.
But yes, a very nice paper. What about the multivariate? I think you said. What about the multivariate output?
The multivariate output is in principle straightforward. All of this extends to sort of higher dimensional range space, essentially, for the Gaussian process. You just make it a multivariate normal for each x. But of course, then you've got again a high dimensional problem. You've got a covariance. This C thing is itself a matrix, okay, for each pair of x inputs, and simply modelling that gets a little bit more complicated. But in principle, that's much more doable than the dynamic thing.
Yes.
You didn't say much about the choice of the regression functions for your mean. Surely the choice of those will highly influence then the covariance and the uncertainty you get in the Gaussian process.
It could do. It can do. I mean, think about it in this way: that when I showed you those plots with the 2, 3, and 5 points, I didn't have any particular mean function in there. It was just picking it up. It will pick it up. Doesn't matter what the mean function is. The Gaussian process, given enough data, will learn exactly where that function is going, and with negligible uncertainty. But if you get a good mean function, it'll pick that up faster. You get better results with fewer model runs. So it can be very important, particularly when you've got relatively slow simulator. You can't do all the runs you'd like to do. Another sense in which it's important is what happens in between the points where you've got the data. Not only does the uncertainty grow, but the mean will tend to revert to the fitted mean function, the regression part. And if that's too far away, if you're having to adapt too far away from where that fit's going, then, and you've got any reasonable amount of space between one point and the next, it won't just nice and smoothly try to go back to the mean and then get pulled back up again. So again, having a good mean function can make a big difference in that respect. If you've got loads of data, it doesn't matter. If you haven't, it's a good idea to try and represent what you really expect that simulator to do. Putting quadratic terms in, or if you think this thing is going to be periodic, putting periodic terms in, or whatever.
Herman, you had a...
Yes, let me phrase my question in Bayesian language. So what if I now have other prior knowledge, for instance, my function f has to satisfy some constraints. Model's complicated, but there's some things I know beforehand. some conservation laws, invariances.
This issue came up yesterday. How do we build in?
How do I build in? So it's not any f, but f has to satisfy. It has to be in some subset of all possible f's.
Like increasing. Positive.
Yeah, it's rather hard to constrain these things to be even just positive, or increasing is a similar thing. One of the references there's a paper I wrote with a lady called Jenny Brynjarzotir about not this problem for the function itself, but for the model discrepancy function. So we then, in order to get a good handle on where the model was deviating from reality, we wanted to put in the fact that we knew as x increased, it was going to deviate further, and it was always going to be below, so it was going to be increasing, negative and increasing. You can't enforce that all the way. What we did was simply enforce a few inequality constraints on some points. So we said this discrepancy had to be 0 at the origin, it had to be negative a little bit further on, and it had to be a little bit more negative a bit further on. Just a few constraints like that made a big difference, but it's try it and see, and it's not a nice throw a tool at it and it work. Keep fiddling. And that was only in one dimension of input, so it isn't easy, I agree.
I mean, there's a classical theory of isotonic regression where the mean function is in some cone or like increasing. I mean, I don't know any papers linking that classical theory with.
Yeah, I meant even more complicated constraint. When x is an input to some PDE solver, and we know that PDE is a balance law, so I know that's exactly satisfied. I don't want any deviation from that, and so on. And that's a function of that state of that PDE. That's my output. But I want that satisfied inside there. So it's a more complicated constraint, just being positive. So
it is more complicated, yes. Obviously, because the thing is very adaptive, if you give it enough data, yet again, it will satisfy those constraints, or that is to say, it will be very close to them. We'll say there's only a little bit of deviation possible from it, but that's not good enough, really, is it? It would be nice to do it properly. I don't know how.
Yes, there is.
Just to continue on this question. So if the invariance that you're interested in results it corresponds to being in a null space of a linear operator, then you can impose it via the covariance kernel.
Yes.
So, and that encapsulates periodicity, symmetries, harmonicity, and a number of others.
Right.
That you can do.
Yes, exactly that.
So, for the increasing monotonicity, there have been quite a number of attempts. So, some rely on discretization and inequalities. Some rely on stepping out of the Gaussian world, and saying instead of having a Gaussian process, I'm having a process that is defined as a linear combination of monotonic functions, and I condition my weights on being non-negative. And then you have something which is truncated.
That's very similar to the isotonic regression.
Exactly.
Yeah, it's much easier if you only have to do this constraining at a lower level in the hierarchy with a lower dimensionality. That's great. But yeah, I'm aware there are efforts of that kind. I've not taken too much.
There was something came through from early in the week. I think it was Pete or maybe it was Jim who said this confidence band you have, the pointwise, and several people said, well, it's a bit conservative. I mean, is there any way you think of making that more accurate in terms of describing you the uncertainty? This confidence is about uncertainty, so that band is very important.
It should not be conservative. I mean, there's again, I haven't mentioned it in here, but there's another paper about actually validating your emulator. So you build it on some runs, you make predictions of future runs with it, and then you can check whether the future runs lie within that bound in the distribution that they should. If it's too conservative, then you'll be finding the truth lies too close to the mean in all of these predictions.
But then you go back and correct the...
Yes. Yeah. So you're learning something from doing that, but you have to go back and work out what it is that's
or
not right.
bootstrapping on.
Yeah, and things never validate perfectly, because you know, the assumptions of the Gaussian process and all of the stationarity and things that you put in are for convenience, and reality is not as convenient as you'd like it to be.
But,
I wanted to ask something about the choice of the correlation function. You were mentioning both the Gaussian and the Mattel and pointing out like the difference in terms of the regularity and the regularity that they also of course yield on the different paths. But both of them, for example, have the property that they only allow a positive covariance correlation between two different points. Have you ever used any other correlation that instead allows also negative values? Or have you read anything in the literature about possible?
No, I'm very much aware that there are many other covariance functions that you could use. I'm struggling to think about a situation, but maybe it arises. Hasn't risen in my world where you think a negative correlation would be appropriate. I mean, obviously, neighbouring points from smoothness will do that. We are talking about something further away, and maybe where there has to be some compensation of the kind you're saying, maybe that for some x's, if it's high here, then it must be lower for others. Yeah, I don't know. I've not met that, but it'd be very interesting, wouldn't it?
Cosine.
Yeah.
Cosine.
Does it still yield a positive definite matrix?
Yes.
That's the problem. Of course, each time you have to think
wavy
about
process.
it. Okay.
Ocean wave.
I'm sure it's easy to construct us. Any other comments? Otherwise, I might point to somebody.
You mean you've got nothing to say yourself, Henry? That's unusual.
I said about treating of people. What? You see, it works. Only if you have to get.
From an applied mathematician who doesn't know very much about Gaussian process emulation, thank you very much. I think I'm now starting to understand more. In the past, you've written things and been quite outspoken about the kind of surrogate stuff the applied maths community does and statistics community, and it's been a sort of interesting topic of conversation behind the scenes this week. You know, a lot of people have kind of done comparisons now between Gaussian process emulation and polynomial chaos approximation, or stochastic alerted approximation, as we might call it. In the applied math community, there are other kinds of, even this word surrogate I'm not quite comfortable with, but other kinds of, I think, surrogate techniques that we use. Another one is stochastic collocation, and that is an interpolator.
Good. But it still doesn't have uncertainty on it.
No. Well, I'm not saying you can't get something, but that's not something we typically worry about. We typically do our job as...
Excuse me. If you work in this field of uncertainty quantification, shouldn't you worry about uncertainty?
I'm not saying we shouldn't do it. Don't misquote me.
Right,
What I'm
okay.
saying is,
This is a real
this
fight.
is what
we want.
this is what we typically do, and as a criticism we can direct at ourselves, and I'm perfectly guilty of this myself. What we typically tend to focus on, and I think it's important that you realise that, you know, just so we can have a constructive dialogue, is you know, what we tend to focus on, and where we often give our talks, is we're focusing on how we just get that approximation, be that polynomial chaos or stochastic collocation or reduced basis or whatever, and our sort of motivation is trying to do that as efficiently and accurately as possible in whatever sense that we define that. But there are various things that we do, and we talk about what's best for the emulation. And I agree that this offers you something that you don't get with other methods for sure, which is very important in certain quantification context. But my real point is that stochastic collocation is an interpolator.
That's absolutely right. And I do sometimes come over as rather outspoken. This is true, and that's just a device. It's the device to create the discussion and to get people to want to argue with me. I'm very good at actually seeing other people's points of view as well, and I do understand that these tools have a lot of application. In particular, if you're trying to do this in high dimensions with the Gaussian process, and particularly with the Gaussian correlation function, you're going to run into all kinds of numerical problems. And some of those tools are great for big, they scale much better than this does. So I'm thoroughly recommending that as well.
Rich, you had a...
So you mentioned your highly influential paper with Mark Kennedy. It's been mentioned a few times earlier in the week, where you took a...
yeah, it's one of these square bracket things in here.
yeah. But when we take a parametric simulator, it's a finite dimensional, bolt on kind of a infinite dimensional non-parametric Gaussian process, and that kind of corrects everything. So it's obvious that can work for prediction. Do you think it works well generally for inference for your finite dimensional parameter in the simulator?
Yes, that's the point. That's the calibration problem. That's what it's there for. So yes, it's important that we recognise that predicting reality is different from predicting the output of the simulator, and that is an important step. So this is very important for prediction. But what bothers me is that people go and try and do inversion or calibration of these models without recognising that, and they will just produce ultimately meaningless parameters that don't have physical meaning from that. The only way to get your physical meaning for these parameters is to somehow understand that model discrepancy uncertainty. So yeah, it's very important. That's what the paper with Brignoud's is all about. And it isn't easy, because no matter how hard you try, no matter how much you put the constraints in that we did there, you will still find that you'll get things wrong, simply because there is this unresolvability between the model discrepancy and the calibration parameters. In order to resolve that, you've got to have information about one or the other, and model runs don't give you that. So it's only from prior information that you can resolve that unidentifiability.
Yes, Peter.
Welcome up, man. You stressed the fact that the emulator's an interpolator of the data. A lot of people put a nugget term, a white noise term on, for numerical reasons or for other reasons to cope with dimension reduction, such that it stops being interpolated. Would you like to comment on these?
Yeah. So a couple of reasons why they do that. As you say, one is numerical stability. When you've got a lot of runs and you're using a correlation function like the Gaussian, which is associated with differentiability, then as you get points close together, the covariance matrix of that becomes almost singular, and that can cause all these numerical problems. So simply putting that little bit of noise on the diagonal of that matrix makes it much easier to get numerical answers out from that. And provided that's small enough, obviously, then it's almost an interpolator, and you've almost got no uncertainty at that point. And that's a whole lot better than having perfection that actually is numerically all over the place, and you've got a perfectly wrong answer in some sense. So yeah, they do that. Another reason, of course, is that some simulators do have noise in them, either because they are stochastic in themselves, or because you're getting so close to the detail of this thing that numerical computation rounding starts to matter. So yeah, there are perfectly good reasons for doing that. And as you say, what happens then is it's not an interpolator, it's a smoother of the points that you've got, going close to them and producing some smooth results in between.
Fantastic. So I think anybody who's desperate to I've got about 15, but I'm not. All right. So thank you very much.
Thank you.